Hello friends and welcome to Shri Tech Education YouTube video channel. In today's lecture we are going to study what is damping, what are different types of damping, and how to find the frequency of free damped vibration in case of viscous damping. So let us start. What is damping? Now damping is the dissipation of energy from a vibrating structure, or the damping is restraining of vibratory motion such as mechanical oscillations or noise by dissipation of energy. Now damping generally we can call the resistance to the vibration or dissipation of energy from a vibrating structure. The term dissipation is used to, that means a transformation of mechanical energy into some another form of energy, and therefore removal of mechanical energy from the vibrating structure. In vibrating system, the effect of friction is referred as a damping. Now in below two animations, we are observing that in first animation there is one spring, one damper attached to mass, and one disturbance is given to mass. When disturbance is given, then system will vibrate, oscillate about its mean position, and due to damper this oscillation get restrained or resisted due to this damper, or the energy is dissipated by this damper, and after some interval of time it becomes steady. In second animation I have shown one mass with a spring and another mass with spring as well as one damper. Due to this attachment of damper, the vibratory motion stops after particular interval of time, which is less than spring and mass only. You can observe that one time versus displacement graph is there. In case of only spring and mass, that displacement continues for infinite number of time. But in case of spring, mass and damper shown by red color graph, this graph is fluctuating and becomes steady or becomes zero displacement after certain interval of time. This is without damper and with damper. This is the advantage of damper. You can reduce the vibrations with the help of damper. Now, there are many types of mechanical damping or mechanical dampers, and these are viscous damping, Coulomb's damping, or it is also called as a dry friction damping, solid damping or structural damping, that is also called as a material or hysteresis damping. Fourth is a slip or interfacial damping. Fifth is magnetic damping. That is also one of the type of damping. That is not a mechanical, but it is one of the type of damping. Now these five types of damping we are going to study one by one. First is viscous damping. The damping provided by fluid resistance is known as a viscous damping. It is encountered by the bodies moving at a moderate speed through the fluid media like air, gas, water or oil. In this viscous damping is provided by any kind of fluid media. This is the most commonly used damping mechanism to reduce the amplitude of vibration. This type of damping leads to resisting force which is proportional to relative velocity of vibrating body. Therefore I can write the damping force Fd is directly proportional to the velocity of vibrating body. This velocity I can write as a dx by dt, first order derivative of displacement x. Therefore I can write Fd is equal to c into x, where the c is any proportionality constant, that c into x dot, there is x dot, that means first order derivative of that displacement x. Fd is equal to c into x dot, where c is a constant of proportionality and is called as a viscous damping coefficient or coefficient of damping with the dimensions of Newton second per meter. C is a damping coefficient. Now the fluid dashpot damping. Same damping is used in our shock absorber as well. A dashpot is there called as a damper. A dashpot is a mechanical device, a damper, which raises the motion via viscous friction. The resulting force is proportional to the velocity but acts in opposite direction, slowing the motion of absorbing energy. It is commonly used in the conjunction with a spring. Therefore, we are always showing with the mass, spring and damper, which acts to resist the displacement. Now, there are many applications of viscous damping, such as door closure, dampers and shock absorber, automobile shock absorber. Large forces and high speeds can be controlled by the dashboards. For example, aircraft carrier decks. There you can observe this dashboards, that means viscous damping. Now, second type of damping is Coulomb's damping or dry friction damping. In that diagram also you can observe, to the mass, displacing mass, one spring is connected and that mass is mounted on the surface, dry surface. So what is Coulomb's damping? This type of damping arises from a sliding of a dry surfaces. The friction force is nearly constant and depends upon the nature of sliding surface and normal pressure between them, as expressed by the equation of kinetic friction, F is equal to mu into N. Here, in case of Coulomb's damping, dry friction is there between the surface and vibrating body. So we can give this kinetic friction force F is equal to mu into N, where mu is coefficient of friction and N is the normal force. Therefore, this friction or damping depends on coefficient of friction and the normal force. This is second, Coulomb's damping. Third is the solid or structural damping. It is also called as a hysteresis or hysteretic damping. Now, in this solid or structural damping, this is due to the internal friction within the material itself. The damping caused by the friction between the internal planes that slip or slide as the material deforms is called as hysteresis or solid damping. Now, in case of any material which is vibrating, its internal planes are restraining or opposing to the motion. This type of resistance or damping is called as a structural or solid damping. Now, this is also called as a hysteresis damping. Why? Because if you draw a stress strain diagram, then for loading and unloading, this curve will not be same, it will be differing from each other, and this type of differing curve is called as a hysteresis curve, isn't it? Now, the stress strain diagram for vibrating body is not a straight line but forms a hysteresis loop, as shown in this diagram, the area of which represents the energy dissipation to molecular friction per cycle per unit volume. So this is the third type, solid, structural or hysteresis damping. Fourth, slip or interfacial damping. Energy of vibration is dissipated by microscopic slip on the interfaces of machine parts in contact under influence of load. Now, under fluctuating loads, the parts of machine which are in contact, this get slide over each other and create a resistance to vibration. This type of resistance to vibration by their own part under fluctuating load is called as a slip or interfacial damping. The microscopic slip also occurs on the surface of the machine elements having various type of joints. The amount of damping depends upon the surface roughness of the mating parts, the contact pressure and amplitude of vibration. This is slip or interfacial damping. Last, fifth type is magnetic damping, a phenomenon that has been observed for many years, by which vibrating, oscillating or rotating conductors are slowly brought to rest in the presence of magnetic field. Now, in magnetic damping, damping due to eddy current set up by the moment of system in the magnetic field is there. There is a resistance to the vibration due to eddy current which is set up in the magnetic field. This is the last type, magnetic damping. These are the four types of damping we have seen: viscous damping, Coulomb's damping, structural damping, interfacial damping, and magnetic damping. After these types of damping, we will study how to find the frequency of free damped vibration in case of viscous damping only. What is the frequency of free damped vibration? Now consider a spring, mass, and a damper system having these three parts: spring, mass, and damper. Now we are studying how to find a natural frequency of free damped vibration in case of viscous damping. As we have already studied, what is viscous damping? In case of viscous damping, damping is provided by the fluid resistance, is known as a viscous damping. Now consider that a vibrating system is there as shown in figure, in which a mass is suspended from one end of the spring and another end which is fixed. The damper is provided between the mass and a rigid support. Now to study the vibration of this system, the following assumptions are made. The first assumption is the mass is rigid and has no damping. That means it is not having interfacial damping. Second, the spring is massless and has no damping. Spring is also massless. It is only having a stiffness. It has no damping. Third, the damper has neither mass nor elasticity. It does not deform. It doesn't having any mass also, but it is having coefficient of stiffness, C. Now let us consider that m be the mass suspended from the spring, yes, or it is also in some cases we are calling it as a K, as a spring stiffness. X is displacement of mass from the mean position at time t. Delta is a static deflection of spring. C is the damping coefficient of damping force per unit velocity. Now therefore damping force, since the viscous damping it is there and it is assumed that the frictional resistance to the motion of the body is directly proportional to the speed of movement. In case of viscous damping we have studied that force is directly proportional to velocity. Therefore damping force or frictional force on the mass acting in opposite direction to the motion of mass is equal to C into dx by dt, and the accelerating force on the mass acting along the motion of the mass is equal to m into d2x by dt square. In that free body diagram also observe that accelerating force is in downward direction. One force due to spring, it is there in upward direction, it is equal to s into x, where one more force is there due to frictional force acting in opposite direction of motion of mass is equal to C into dx by dt. Last, spring force on mass acting in opposite direction to motion of mass is equal to s into x. Therefore the motion of mass, now equation of motion of mass I can write is equal to accelerating force is equal to sum of these two forces. Negative sign indicates the force is in opposite motion. Therefore rearranging these terms I will get one equation where I have done one star mark. It is equal to d2x by dt square plus c by m into dx by dt plus s by m into x is equal to 0. Now this a system described by this equation is said to be a single degree of freedom harmonic oscillator with a viscous damping. A single degree of freedom system with a viscous damping. Previously, in some previous videos, we have studied one spring and mass system. In that we have got this equation of motion as d2x by dt square plus s by m into x is equal to 0. This is the single degree of freedom equation without damper. Now here with damper only one term has added, that is equal, what is added? Plus c by m into dx by dt. That term is added in that equation of motion. Now due to this term, this is the differential equation of second order. Assuming the solution of this as x is equal to e raised to kt, where k is a constant to be determined. Now above differential equation reduces to, if I put x is equal to e raised to kt, I will now further I am going to find the solution of this x, so that the solution of this differential equation I can get. Therefore this equation turns to be k square into e raised to kt plus c by m into k into e raised to kt, that is first order derivative of that x, plus s by m into x, where x is e raised to kt. Now rearranging the terms and some cancellation of terms, we will get one equation k square plus c by m into k plus s by m. Now this is the second order equation, differential equation, whose solution we can find in as a k is equal to plus or minus minus b plus or minus square root b square minus 4ac divided by twice a. Therefore find the value of k. I am getting these values of k as k1 and k2. Once put value as a plus, once put value as a minus. Therefore k1 and k2 values I have got. Now the most general solution of this differential equation, first differential equation, this with its right hand side equals to 0, has only complementary function, and it is given as x is equal to c1 into e raised to k1t plus c2 into e raised to k2t, where c1 and c2 are the two arbitrary constants which are to be determined from the initial conditions of the motion of mass. Therefore it may be noted that this k1 and k2 may be real, complex conjugate, or equal, isn't it? Now here see that second equation, the solution of this equation, differential equation made by star, can be written as x is equal to c1 into e raised to k1t plus c2 into e raised to k2t. Now c1 and c2 are arbitrary constants which can be found by putting initial conditions in the equation of motion, where this k1 and k2 are there. If these k1 and k2 are real, the condition will be something different. If k1 and k2 are complex conjugate, the damping condition will be something different. And if k1 and k2 are equal, then there will be some condition will be different. Now we will discuss these three cases. In these three cases, we will assume first when the roots are real, the roots, these k1 and k2 roots, if they are real, that means these are having some positive value. Now when these k1 and k2 will be real, when the square root value in the square root, what is there, c by twice m square minus s by m. If this c by twice m square is more than s by m, then these two values will be real. K1 and K2 will be real but negative. There may be negative chance, but they will be real. This is the case of overdamping. This condition is called as overdamping. When these roots K1 and K2 are real, then it is called as overdamping or large damping. So what is overdamping? Whenever these roots of this differential equation are real, then this condition will become overdamping, and overdamping means a large amount of damping will be there in the system. In case of overdamping, I have shown one animation at the bottom. In that you can observe that when this damping provided to mass is having a large amount of damping coefficient, in that case this type of damping will become overdamping, and this mass comes to its initial position quickly as there is a large damping. When the mass moves slowly to the equilibrium position, not quickly, mass moves slowly to the equilibrium position without oscillating about its mean position. This motion is known as a aperiodic motion when the roots are real. Now if the roots are real, then I can write x is equal to c1 e raised to k1 into t, put the k2 and k1 values. But in actual practice, this overdamping condition is avoided because the mass comes slowly to its initial position without oscillating about its mean position. So this overdamping condition is also neglected or avoided. Second condition is there when the roots are complex conjugate. When the roots are complex conjugate. Now when it will be complex, when in that equation of k1 and k2, the c by twice m value is less than s by m, then square root value will become negative, and when square root value becomes negative, then the answer will become a complex conjugate. Therefore if s by m value is greater than c by twice m square, then the answer or roots becomes negative. That is, sorry, the roots will become a complex conjugate. This is the most practical case of damping, and it is also known as under damping or small damping. In that animation I have shown under damping. In under damping, the mass comes to its original position slowly with fluctuating about its mean position, and this is the most practical condition, and this is used in various applications such as our shock absorber in all the four-wheel drives or two-wheel drives as well. So if the k1 and k2 are complex conjugate, then we are assuming some things, that is c by twice m is equal to a, small constant a, s by m is equal to omega n, you are knowing that omega n square, and this square root value is equal to omega d, and omega d is equals to now s by m, we are knowing it is a omega n square, circular natural frequency, omega n is circular natural frequency, and c by twice m we are assuming it as a small a. Remember these two submissions, what we are putting here, c by twice m is equal to a and s by m is equal to omega n square, omega n square. Therefore omega d, damped circular frequency, will become now square root of omega n square minus a square. Omega n square minus a square is omega d. Now if this is omega d, that is circular damped natural frequency, then we know that the periodic time of vibration, time period Tp, is equal to twice pi upon omega d is equal to twice pi upon square root of s by m minus c by twice m square is equal to twice pi upon omega n square minus a square. And frequency of damped vibration is equal to fd is equal to 1 upon time period is equal to 1 upon twice pi square root omega n square minus a square. Remember this formula for frequency of damped vibration with damper. Fd is equal to 1 upon twice pi square root omega n square minus a square. Now if suppose, note that when no damper is provided, that means damping coefficient c is equal to 0, then in this formula if you put value of c is equal to 0, then frequency becomes 1 upon twice pi square root s by m minus 0. Therefore frequency will be fn is equal to 1 upon twice pi square root s by m, and this is the frequency of free vibration of spring and mass system. That means free vibration, natural frequency of free vibration. With damper, just one term is added, 1 upon twice pi square root s by m minus c by twice m square bracket square, c by twice m bracket square. So remember this formula for frequency of damped vibration. In that, these two submissions also you have to remember, c by twice m is equal to a and omega d is equal to square root omega n square minus a square. These are required for further calculations or while we are solving numericals. Now next, when the roots are equal, then if suppose in this equation of k1 and k2, if c by twice m square and s by m, these values will become equal. Now this square root value will become 0. If these roots are equal, in that case then the radical becomes 0 and the two roots are equal. Now k1 and k2 will become equal. This is the case of critical damping. In case of critical damping, the object or this mass will come rapidly to its original position in case of critical damping. So in other words, in critical damping is said to occur when the frequency of damped vibration is 0. When these roots are equal, frequency of damped vibration is 0. The motion is also called as aperiodic. This type of damping is also avoided because mass moves back rapidly to its equilibrium position in shortest possible time. But in some cases we require this condition also, critical damping. That is, I have shown below this animation one term or one node there. This is often desired for the damping of a system such as doors. In that door, one damper is provided so that once you open the door and it will immediately close whenever it is released, due to critical damping provided there. Now put the values there, two equal terms, then you will get c by twice m square is equal to s by m. You can put value of c as a cc because the critical damping coefficient may be obtained by putting cc for c as a condition of critical damping. Then you will get value of cc as cc, that is critical damping coefficient, is equal to twice m into square root s by m, that is twice m into omega n. You have got cc is equal to twice m into omega n. Remember this formula as well for calculations in the numericals. Critical damping coefficient cc is equal to twice m into omega n, where omega n is square root s by m. Now this critical damping coefficient is the amount of damping required for a system to be critically damped. This cc represents amount of damping required for a system to be critically damped. That means to come its original position rapidly. So we have seen the three conditions for damped vibration as overdamping, critical damping and underdamping, from which underdamping is most preferable in various applications. That is third condition shown by the blue graph. By red graph I have shown critical damping, and by green graph I have shown overdamping. In case of overdamping, mass comes slowly to its original position without oscillating about mean position. In case of critical damping, mass comes rapidly to its initial position. In case of underdamping, mass comes slowly by oscillating about its mean position. After a certain interval of time it comes to its initial position in case of underdamping. So each one has its different application, but most preferred is underdamping condition. So thanks for watching this video. In next video we will study or we will solve some problems as well. So thanks for watching the video. Subscribe the channel.